Here we go, folks. This is very much an HL question, definitely a classic. So if you haven't tried one like this, please take the time over it. We've got monochromatic light with a wavelength, excuse me, and we're told the adjacent lines of the diffraction grating are separated by a certain distance. We want to know how many diffraction maxima are present in the transmitted light. In other words, how many diffraction maxima can we see when we're using this diffraction grating? As I say, you'll have seen this in different forms, perhaps slightly different with a different presentation. However, it's very much a repeat of many similar questions, and I'll try and find some more that I can link to this video. So, usual story, please press pause, and then when you've had a go, hit play to see the explanation. Okay, so we're dealing with a diffraction grating here. We're going to use our equation n lambda equal to d sine theta, and we're going to ask ourselves, do we know any of this stuff, and what are we asking to calculate? We're going to be calculating numbers of diffraction maxima, I should say, and so therefore we want to calculate this n. Now, of the other ones, we may not feel like we know them, but we do. Okay, firstly, we know that d is equal to 2.8 times lambda. Okay, d is 2.8. We're told that that's the distance between those lines, 2.8 lambda. We also know theta, because when we're trying to determine the number of maxima we can see, we'll firstly think about the maximum angle that we can possibly see. The maximum angle is going to be equal to 90. So therefore, the sine of that angle maximum is going to be equal to 1. We're then going to put these numbers in. We've got the maximum n that we could possibly observe is going to be d sine theta max over lambda, and you notice we've got d equal to 2.8 lambda, we've got sine theta 1, I've kind of neglected to put them in, but we get 2.8. Now here's the difficult bit. A lot of students at this stage would round up. This is one of the few occasions that you round down, because remember, this tells us the maximum possible n we could see. Now, in order for us to see an n, we have to cross over the integer value. So if this is 2.8, means we can see n equal 1, it means we can see n equal 2, but we've not reached 3 yet, so therefore we cannot see 3. So we must leave this as a 2. So a lot of students at this stage would answer 2, however there's more to it. Remember, we have a diffraction pattern with a 0 order maximum, which is not included, and also they're on either side. So when we want to observe the maxima, we take 2 times that n maximum, we add 1 to it because that of the central order maximum, which is 5, and so the answer here is 5. Now, a small point here would be that a sort of quick check and a way of confirming your answers is that the number of maxima is always going to be odd due to that relationship 2n max plus 1. We get an extra 1 from the central order maximum, so that number 2 is automatically wrong. Okay, which then allows us to then think of which one is correct here. As I say, I've seen this question in various different forms. It's very much a classic question, so hopefully one which will come up in your exam.